Welcome to another invigorating episode of Empowering Introductory Algebra. Hi, I'm Bob Young, Assistant Professor of Mathematics at Brevard Community College. With the help of the WBCC TV crew, we have developed this series to assist you to gain an understanding of introductory algebra leading to those college-level courses. We will bring you main ideas of key algebra concepts, tons of examples, great graphics, and study tips to help you to become the best mathematics students possible. Let's continue our adventure. Now, in the last episode, we were discussing solving those rational equations, so let's go to the graphic here just to make sure that you got that down in your organized math folders that we're hoping you keep throughout these lessons. And we found to solve a formula for a given variable, the 5 steps, which I'll just run through quickly again. 1, always know what you're after, know what you're trying to solve for. Identify the variable you want to get by itself. 2, multiply both sides of the equation to clear fractions if you have them, if necessary. And since we're discussing rational equations, you most likely will have some formulas with the fractions. 3, get all terms with the variable to be solved for on one side of the equation and all other terms on the other side. And step 4, look to multiply to remove parentheses or factor out a common variable. And if you remember in that last episode, we did have one that we had to factor in order to solve. And step 5, solve for that variable in question. So let's look at some more examples here. And we will find that we have formulas involving rational equations. In this case, we have a divided by p equals 1 plus r, and we want to solve this for a. So in order to do that, we need to multiply the equation through by the common denominator, which in this case is the only denominator of p. So we will go ahead and multiply everything through by p. So p over 1 times a over p would be this side here, distributing the p through. And you can see the p's will cancel out, leaving us with a here, equals over here p times 1 plus r. All right. And now we can leave that answer p times 1 plus r this way. Now remember, we talked about this in the last episode, that this is not only used in math using formulas like this, but in a lot of your science classes. So there might be a case where you know what r and p are, or maybe you don't, but which one you'll plug in for. It may be easier to plug in this form, or it may be easier to distribute here and get p plus p times r. All right. So, you know, sometimes in science, depending on how the problem's worded, this will work. These two are the same. We know from our friend the distributive property. So that one kind of fell right into our lap just by multiplying through by the common denominator. So life is good. All right. Let's look at one more here that looks a little bit more formidable. We have b equals a times t minus h, all divided by t, and we want to solve for t here. So again, we want to get rid of those fractions by multiplying through by the common denominator, which in this case again is the only denominator, t. So when I multiply by t, I get b times t equals, what happens over here? You know what? The old chop chop, the t's go out, and we're left with a times t subtract h. Now this is one similar to the last episode. We're after t, but we have t's on opposite sides of the equal sign. See, so don't just go dividing by b here to get t, because you have more than one t. Be careful there. That's a key point. All right, so what we're going to do is to get all these t's together on one side by subtracting the a times t from both sides. So let's show that step here, because you know on the BCC network we spell this out for you as best we can. So we end up with b times t subtract a times t equals what over here? H. Now don't forget something on that h. I left something hanging. A lot of students make this mistake. What kind of minus? There's a minus h. That's a negative. Same thing, minus h. Be careful. Now These aren't like terms, Young. I can't put them together, but I can factor out, since I see t's in common here, I'm after t, take out that common t, and that will leave us with b minus a equals the minus h. All right, so to get t by itself, to take out multiplication, attack with division. So you can divide both sides by the b minus a. Okay, so t then would equal a negative h divided by b minus a, but again in science class you may not like that. It has a lot of negatives in it and stuff, doesn't it? The h is negative, you have to subtract the a, so you might see the same answer in certain algebra books look like this. They might write it as t equals h over a minus b. These two answers are the same. Now, Young, how did you do that? How did this fraction become this fraction? Well, in order to take that negative off the h, you know what I had to multiply by to get the h there? I had to multiply by a negative 1. And since these are fractions, whatever you do to the top, you must do to the bottom. And not only did I multiply the negative 1 through the bottom, which changed the signs, then I went ahead and I used my commutative property and rewrote the order. See, so I think I would rather have this than what we ended up with over here. I think this has less minus signs, would be easier to plug numbers in for and get. All right, so be careful on how you write things in algebra. You know, there's sometimes more than one correct way to write the same thing. I don't want you to get out there and get this answer and look in the back of a book or something and see that and say, man, I must have did something wrong. Sometimes they'll just multiply to take out some negatives in there. So a little bit of caution to the wind there. Alrighty, now back to the graphics. It's time to start a new topic. I'm tired with these rational expressions and rational equations. It's time to pick up something new, and we're going to talk about square roots next. So this is entitled Introduction to Square Roots and Radical Expressions. We're going to get radical, man. So the first thing I want to talk about is parts of a radical. Parts of a radical. Now notice the little number there. It almost looks like a division symbol here. Let me bring my hand up. I haven't used the hand in a few episodes here. This radical symbol that the hand is waving around kind of looks like a division symbol, doesn't it? But it's not. It is called the radical. Now going over here, the hand is moving. The number 2 here is called the root or index, okay, of the radical. Now on square roots, they never write them in most books. It's understood. So you won't see a square root with the 2 in there very often. And what's underneath here inside the radical, the 12a to the 4th b to the 6th power c, is called the radicand. The radicand is inside the radical. Wow, man. The radicand is inside the radical. All right, so we will go to some examples here with square roots and parts. All right, I gave you the square root of 49. So the root or index of this radical, and on most square roots they never write it, but it's there. It's kind of like hidden, but it's there, is a 2. The radical symbol we talked about is that funky thing. It's not a division, it's the radical symbol. And what's underneath here is called the radicand, which is 49. So boy, my students used to love if I ask them what is the radicand of something on a test, because that's just what's underneath the radical. Okay, now let's look at some more things here. And the number b, this is the strict definition of square roots. The number b is a square root of a if b squared equals a. Now some of you out there are looking like, Young, that's nice, but it doesn't really do it for me. It doesn't ring a bell here. So remember, whenever you see something like this when you read your algebra book, and that's what algebra books are full of, is just statements like this, remember what a and b are. They're numbers. Plug in some numbers if it makes sense here. So what we can say is, how about this one? The number 4, we'll put 4 in for b, is a square root of a, we'll call a 16, if b squared equals a. And in this case, I think that'll make perfect sense. If 4 squared equals 16, because remember 4 squared means 4 times 4. So it makes a little bit more sense when if you plug numbers in, if you go to read your algebra book and the variables just make no sense. All right, let's look at the next graphic here real quick before we go on here. And this is entitled Simplifying Square Roots. Now notice it states, and please get this down in your notes, that every positive number has 2 square roots. For example, the square roots of 9 are 3 and negative 3 based on what we just discussed there, because 3 squared equals 9 and negative 3 squared. If you take negative 3 times negative 3 equals 9. All right, the positive square root is called the principal square root. So when you see here goes the hand moving again, when you see that radical symbol used to represent a square root, it represents only what's called the principal square root. So when you are after the principal square root, that's the one with the radical, it's going to be the positive part. So let's go back to the examples here and illustrate. In some textbooks, they'll say find the square roots, and if you're a good English student or communication in the comm, roots, plural, more than one. So if you're after the square roots of 9, it would be 3 or negative 3 would be the square roots of 9, or 3 and negative 3, whichever way you want to say it. 25, 5 or negative 5. And 64, 8 or negative 8. But if they say find the principal square root, now that's the one containing the radical symbol, all we're concerned with is the positive answer. So when you see the radical symbol used, the square root of 9, you don't say 3 or negative 3, just 3. Just the positive answer. Huge. Square root of 25, 5. And the square root of 144, 12. And what you're asking yourself here is, what if I multiply it by itself? Gives me this number. This multiplied by itself gives me this, and so forth. All right, when you discuss radicals. And let's continue with that thought here. You can check these square roots. The square root of 36 is 6, because if I take that answer and I raise it to the root, now remember the root over on these square roots is 2, you get the radicand. So the square root of 36 is 6, because 6 squared is 36. Square root of 100 is 10. Why? Because 10 squared equals 100. So really what square roots do is that they undo squares. Like again, you could say the square root of 36, we could write that as the square root of 6 squared, couldn't we? So that square root undoes the square. It takes it out, and you can square the answer to check it. Pretty neat, huh? But you know this is algebra. It's not just all numbers. But Young, what about variables? People start getting scared. Don't panic. The square root of x squared is x. Why? Well, because if we take the answer and we square it, do we not get what's in what I call the cand? In this case, the radicand. So it's in there. Makes sense. Okay. What's the square root of x to the 4th? Well, what times what gives me x to the 4th, or what squared gives me x to the 4th? It would be x squared. So to check that, you can say that if I take x squared and square it, do I get what's in the radicand? You're darn tootin'. And remember, looky here, Young, some power rules happening here. We've got power rule number 5. When you raise a power to a power, multiply the powers. All right? Some people don't think that you can take the square root of x to the 6th, but you sure can. The square root of x to the 6th is x to the 3rd. And why? Well, if I take x to the 3rd times itself, whenever you multiply same bases, you add the powers, you get what's under here. X to the 3rd times x to the 3rd would be x to the 6th. Or if I take x cubed, or x to the 3rd, and I square it, multiply the powers, there it is. There it is. Now, are we seeing a pattern here so far? Something to do with the root and the power. 2 into 2, we had 1x. There's a root there. 2 into 4, 2x's. 2 into 6, 3. Interesting, Young. So it looks like there is a profound impact between the root and the power. It's like cutting it in half. It's taking those squares out and putting what's left. So let's look down here. Some people might go, my gosh, Young, you're jumping from here to here. That's scary. If you think about the little 2 in there, the square root of a12 b30 would be, cut it in half, a6 b15. So all that square root took out a bunch of squares in there and left this. And again, you can check it, because if you take this answer, a6 b15, and you square it, you know what you're going to get when you multiply the powers? The radicand, what's under there. So these make perfect sense. I mean, they fit like a glove. So to check a square root answer, square it, and you better get what you started with, because square roots undo squares, and we're going to find squares undo square roots. This is great stuff. You know, Young, he's always going to check your stuff here. Now, how about one like this, minus the square root of 25 versus the square root of negative 25? Wow. Now, let me think about it. Let's do the bottom one first here. Now, try this on your calculator if you have a calculator at home. Do the square root of negative 25, and your calculator is going to go, Well, it may not do that, but it's going to say error. I guarantee you it's not going to like it. Because you know what y'all are asking your calculator? You're asking your calculator, hey, calculator, what number squared is ever going to give me a negative 25 under here? Because that's how I just said we checked answers. Now, if you think about it, no matter what number, whether it be positive or negative, when I put it in here and square it, what's it going to come out? So the calculator is going, So in the real number system, if you try to take the square root of something negative, if the radicand is negative, all you can do is write no solution. It will not happen. Bad. But up here, the negative is on the outside of the radical. So really, what this is saying is it's like a negative 1 times the square root of 25, and that's going to give us negative 1 times 5, the square root of 25 is 5, to give us a final answer of negative 5. So it's okay if the negative is outside the radical, we can go ahead and get the answer there. But this one, and your calculator will verify, I don't think so. All righty. Or let's mix some variables and some numbers together, some variable vermin and some numbers. Yeah, so we can go ahead and get some of this stuff going here. So the square root of 4a10b4, does that scare you? It shouldn't. You can say the square root of 4 is 2. And what do you do when you're after those variables? I think variables are easier than the numbers. Cut them in half. a5, b2. All right, so the square root of 4, a to the 10th, b to the 4th, this, you could square that, it will check. All right, the square root of this quantity, 8xy raised to the 8th power. Yeah, you could take the whole quantity and cut it in half if you wanted and say that's, well, 8xy raised to the 4th. Yeah, so it works that way. Even when they get nastier here, the square root of y plus 9, quantity squared, you could write as just plain y plus 9 to the first power, which would be itself, wouldn't it? See, so I like variables even better than numbers when it comes to that here. Now, how about this one, Young? Here's where a lot of people get in trouble. If you try to take the square root across a sum, you are in some deep doo-doo. Like, you can't say it when you have plus signs in here that the square root of 9p squared is 3p. Can't do that. See, and then this one I wouldn't really know how to do anyway, the square root of 12p, because that's not even a nice number, and then 2 here. So notice I put a caution over here. Notice I put a caution. The square root of a plus b, when you're talking plus here, does not equal the square root of a plus the square root of b. Boy, I see a lot of students make that mistake. Now again, this is what the textbook will say, all right? And a lot of people look at it and go, I don't understand. So again, put in some numbers up here. I went ahead and put some numbers in here for the a and b. I let a be, what, 16 and b be 9. So let's think about this. Is the square root of 16 plus 9 equal to the square root of 16 plus the square root of 9? No. Because if we added 16 and 9, what we would have here, I'll just keep going up with this thing, up and away, we'll have the square root of 25 equals the square root of 16 plus the square root of 9, and we're understanding now how to evaluate these radicals. The square root of 25 is 5, equals what? The square root of 16 is 4, plus the square root of 9 is 3. That's why the equal sign all of a sudden becomes slash not equal. Not equal. See, so this does not work. Do not try to take the square root across plus and minus signs, or you will be in deep trouble. So Young, how do I do this if I can't take the square root across plus and minus signs? Did I ever say factoring would go away in here? It's not. we can factor that trinomial, and some of you out there I should be doing this to you if you didn't recognize this. Shame, shame, shame. You should have seen that this trinomial factors because the first and last terms are, those perfect squares. It is a perfect square trinomial, and when you factor it, watch what happens. 3p, 3p, both pluses up here, both pluses here. What times what gives me the 4? 2, 2. So this factors into the square root of 3p plus 2 quantity squared. How about that? So now you can sit there and say, hey, that square root will take out the square or undo it, and it's similar to this example up here, really. So we had to just factor this one, and we get 3p plus 2. How about that? Yeah. So watch out for some of these here, and the caution flag is now up. All right, let's go back to some graphics here for a while. I've been beating you up with some examples here. Let's talk about some things. Now, introduction to square roots and radical expressions. A square root radical expression is simplified when its radicand, what's underneath there, has no factors that are perfect squares. All right, so to simplify any square root, look for what I call the friendly square roots. These are friendlies, like the square root of 1 we know is 1. And why it's 1 is because we can write the square root of 1 as the square root of 1 squared, and that square root takes out the square. The square root of 4, 2. The square root of 9, 3. The square root of 16, 4, and so on and so on and so on. Let me bring the hand back out. Notice where it says so on and down the line. All right? Or here's another nice little trick with square roots. Anytime in 2 here you have the square root of something times itself, think about this. A times A, if you multiplied here, and we're going to talk about this in a second, is called the product rule. You get the square root of A squared, which is A. All right, so any square root times that same square root gives you that number. And we'll talk some more about that. And down here we've got some examples of that. So let's think about this. The square root of 10 times the square root of 10, now would be the square root of 10 squared, or 100. But notice that gets me 10 back. The square root of b times the square root of b, well, it'd be the square root of b squared, which is b. And boy, look at this one. The square root of 1,024 times itself, well, gives you 1,024. All right, so looking at some examples here, this is what's called the product rule. And what the product rule says is if you have the square root of any two things multiplied together under one radical, you can bust them up into itsy-bitsy radicals. So you could take this big radical and bust it up into the square root of A times the square root of B. Or you can take these two and put them together into one. So it works back and forth. Kind of neat. So here we've got the square root of 3 times the square root of 2. So radicals work similar to numbers. The square root of 3 times the square root of 2 using the product rule is the square root of 6. The square root of 5 times the square root of 3, the product rule tells us, is the square root of 15. The square root of 6 times the square root of 7, the square root of 42. Now, isn't that nice? Isn't that nice? So these behave like real numbers. So when you multiply two radicals, you get a radical by the product rule. Now, Young, wait a minute here. What if they slip me numbers and radicals? Well, you take the numbers with the numbers and multiply them on the outside of the radicals. And what this says right here, by the way, is 5 times the square root of 11. See, because there's no plus or minus between the 5 and the radical. So it's 5 times the square root of 11. So we want to get the terminology right here. Let's make a note of this. 5 times the square root of 11. Okay, times 4 times the square root of 2. So 5 times 4 is 20, multiplying the numbers. Using the product rule of radicals up here, the square root of 11 times the square root of 2 is the square root of 22. All right, so it works in that fashion. It works in that manner here. So very good stuff. All right, so we talked about this on the graphic. So to simplify those radical expressions, and now I'm bringing my little look-see-sees here, looks for the friendly square roots. And we talked about these 1, 4, 9, 16, 25, 36, 49, 64, and so forth. Those are perfect squares, aren't they? Perfect square numbers, and these all come out very nice. All right? Or remember the fact that any square root times itself gives you that item squared, which brings it out. All right, so let's think about the product rule again. Why does it work? The square root of 5 times the square root of 5 equals 5. Why, Young? Because if I multiplied that, it would be the square root of 25, or if I did it with exponents, it would be the square root of 5 squared. Either way you want to think about it, you get 5 back. So that's the big thing. I had an old high school coach one time when he did this. He said, you know, any square root times itself gives you that item. He goes, you could take the square root of your mama times the square root of your mama. It don't matter what's under there. And you know what you're going to get? Mama. And some people be out there, Young, don't be talking about my mama now. I'm not going to. I'm not going to. All right, so let's go ahead and look at simplifying some radical expressions using this product rule here. All right, so on the square root of 50, we can break this thing apart into, anyone know a friendly square root that breaks 50 apart? Now, there's lots of things that break 50 apart. You could say 5 times 10, 1 times 50, but to simplify it, we want to look for those nice square root values. So in this case, I think the square root of 25 times the square root of 2 works the best. So when you are simplifying radicals here, you can go ahead and look for those friendly square roots. Now we know the square root of 25 is 5, and we end up with 5 times the square root of 2. Okay. Now you know what this is called out there? This is called simplified radical form. Simplified radical form. Now, gee, Young, I wonder why they call this simplified radical form. Well, it's simplified and it's got a radical in it. You know, math is such a hard thing to figure out. Now, what if I was looking at this and I didn't see that friendly square root, Young? What if I didn't see 25 and 2? What if I came down here and said the square root of 5 times the square root of 10? And then I don't know what either of those square roots are. Man, I'm all messed up now. Well, you could still break that square root of 10 down. If you went ahead and broke this number all into primes, you could say that's the square root of 5 and then break the square root of 10 apart into the square root of 5 times the square root of 2 using the product rule. So look what we have here. We have 2 of the same square roots, and when we multiply them, you know what? The 5 comes back out and we're left with the same answer. All right, so let's take one more here. Do y'all see on the square root of 48, and we'll pick some more of these up on the next lesson. We'll simplify them, even nastier ones. You know, we just don't do the easy ones here. You would take and break that. Do you see a friendly that goes into 48? Let's think about friendlies. 4, 9, 16, 25. Think those perfect square numbers, and in this case, 16 and 3 would be the best case. All right, but you could prime it if you couldn't get 16 and 3 and still get the same answer. So the square root of 16 times the square root of 3 now, you know that the square root of 16 is 4. And we end up with the final answer of 4 times the square root of 3. So the square root of 48 in simplified radical form is this. So, wrapping things up today, you have been given notes, examples, and tips to succeed. Now it's up to you. Take the initiative and work to master all related materials in your textbook. With each concept mastered, your confidence will build. Take care, and we'll see you next time.